the road? Matt, are you going to make an announcement? Great. Because I also have a question for you that I was going to email you, so I can have you. So how about you come up to the front?
Okay. Everyone have their homework 1 grades?
Yes.
All right.
Yes, sir.
There's at least one of you that doesn't because he decided to name weird things like 18.sql. I don't know if he was here. You should probably check his email if he has not, because you're getting a 0 end of the day if I don't get it. Couple things. Let's see. One, please test your queries. I had about 6 of you that gave me things that just went to null. Either for things like UTF-8 code points, meaning you copy and pasted something from another editor, like Microsoft Word or something that does UTF. What else did I find? Also, name your stuff, please. I have about 30 seconds to, if I can find what's wrong in about 30 seconds, I'll correct it. If I can't, I'm going to email and say, hey, send me a zip file with something that actually corresponds to what the guidelines say. All right. There are 70 of you. I spent probably 4 days writing scripts and trying to get your stuff graded. I just finished it last night. All right. Going on, I've got maybe 2 days to kind of devote to this. All right. Make my life easy, I can make your life easy.
In the spirit of making Matt's life easy, for homework 2, where they are writing queries to do things like create views, and also there's one problem where they're told to delete tuples from one relation, old bookings, and put them in a new table. Do you want them to print out so write the command to create the view and then do a select all from the view, or do you just want them to write the view and not print the table that results?
So I would answer, the more information you can give me, the more lenient I can be.
Okay.
If you decide to print off, that's fine. That's great. I will probably have something similar. You can just submit me the view commands. My grade script that I have both compares what your query is and what the correct query is that I have, okay, and the outputs, right? If you say it's, if you give me the outputs, I can say, hey, your query might be messy, but it seems to work. I can give you probably full points on that. If you don't tell me the output, I'll say, okay, I'm not terribly convinced that this works, right? Because you've decided to, put 3 joins and a delete somewhere in the thing where it should just be, update, right? The more information you give me, the more lenient I can be. Make sense?
Yep, makes sense.
If we didn't do that, considering the deadline for extra credit was last night, or essentially this morning, at 6 a.m., is that something we could resubmit with that in there and still get the extra credit, or not possible?
That's Matt's call.
If it was someone else, Adam, I'd say probably not. Knowing you, you're probably fine.
Yeah. That's what he means.
That's on our hand up somewhere in the back.
If you do it, probably put in a comment explicitly saying, this is what I did.
Yeah. Someone else in the back had a hand up. Left side. No. Yeah.
We have a question about one of our things.
The defined thing.
Like you said that I asked if I checked the result on one of the queries.
Yes.
And I didn't miss it all.
Okay. That's interesting because when I ran it, then if I put that in my comment on your grade, it means it produced a null or an error. it shouldn't have done either. So if you,
It's for number 6 where it produces a null because there aren't any things with the current date in the table initially.
okay, well, let's put it this way. You have no guarantee what data I'm going to run. My data is actually completely different. There are several of you that hard-coded one for one of those the queries, and I said, yeah, nice try. You don't hard-code the keys into your queries. That's kind of
A second, I thought that I had specifically mentioned that, but.
Yeah, I would think. Right? But-
I added different data in the
Okay.
table and it showed up different numbers.
Okay. Send me an email your output, and I'll show you what mine does. All right. Yeah.
It says just for the gross hotel.
Mhm.
Can you not just hard code that?
No, because you wouldn't know what the.
You have no clue what the key is going to be. And for a lot of real world data, the key is automatically generated, right? So in some cases, it might be the key is 1. You have no guarantee that that will always be the case, right? Key is the kind of the point is to say if it says the Grosvenor Hotel, well, that's the only thing you can guarantee is that the name will be the Grosvenor Hotel. Right? You have no guarantee that the key will always be 1. As a matter of fact, just so you know, the data that I will be using is going to try and break all the assumptions you might have that you don't know that you have. Over here.
You answered my question.
Okay.
Thanks, Matt. And remember, I will reiterate, Matt has to grade 70 homework assignments. Matt is a 10-hour GTA. So he has at most 10 minutes per homework assignment. So that's not a lot. So try to make his life easy. Okay. Thanks, Matt.
Yep.
Okay. So we are making a bit of a sea change today in where we're going in this course or for the next couple weeks. So it would help, there we go, if I could get back to the lecture notes. So we have been talking about data manipulation language, data description language, how to use them, what's the theoretical basis for them. This is all end user stuff and database administrator stuff. What we're going to be moving into is a different role, which is what happens if you are asked to actually design a database, which is where the big money is. It's not in being able to write queries on a database, but it's actually in designing a database and also designing it so that it helps the query optimizer run its queries efficiently. So for the next 2 weeks, we're going to be talking about 2 different techniques for doing design of a database. One is top-down and is called entity relationship modeling. The other is bottom-up and it is called normalization. I would say that I tend to use both design methods when I create databases. I think the entity relationship model appeals more to me. I'm more of a top-down person. And I use the normalization technique more as a check on my ER diagram, but some of you may be a little more mathematically oriented and find normalization to be more your cup of tea. At any rate, we will go over both approaches to how you design your relations. And then after that, we'll spend a week talking about the physical design of a database, what you can do as far as indexing to make life easier on the query optimizer so that it is able to answer queries more efficiently. Plus, we'll go behind the curtains or the scenes so that you're able to see the physical data structures that database manufacturers like Oracle use to actually store databases, because there are the in-memory techniques that are used with trees and hash tables. They don't work on secondary storage, so instead they use variations of them, and we'll be talking about those variations because my understanding is you don't always see it in 302. Okay. The second thing is there is different terminology used by different people, and in particular the book that we're using sometimes uses terminology that is a little different than the terminology in my slides because I'm working from a separate textbook. I have tried to show what the different terms mean in each of the two. So I'll use my own term, like say strong entity, but then I'll also use the term independent or master entity that the textbook uses. When you draw your diagrams, I expect you to draw the diagrams the way I draw them on my slides. The book doesn't have what I consider to be generally accepted way of drawing ternary, quaternary, anything that's other than a binary relationship. So I expect you to use my diamond structure. When I get to it, I'll show it to you. The rest of it is pretty much the same between the book and my slides. So without further ado, we're going to start with the top-down approach. And that is entity relationship modeling. And the idea is that we have three basic things that we want to create when we're creating a database. We're getting tables, their attributes, and foreign keys. And that is embodied in the idea of entity types, which become relations, attributes, which become columns, and relation types, which become foreign keys. Okay? So the big thing when we're doing top-down design is identifying what are the entities, what are the relationships between the entities, and what are the attributes. Okay, so entities are things that may have a physical existence, like in our dream home. Staff, property, and customers are physical things, or parts. Suppliers and products are physical entities. Entities may also have a conceptual existence, but I will warn you that when they have a conceptual existence, they often are a relationship. So a viewing relationship of a customer views a property, while that will be materialized as a relation, it actually is a relationship. Same thing. We may have an inspection. A person inspects a workplace or a branch. Again, inspection will probably end up as a relation, but just because something is a relation doesn't mean that it is an entity. So I tend to make a distinction between something that in some sense has a physical independent existence and something that depends on the existence of other entities. So with entity relationship modeling, you typically are drawing diagrams to represent the database design. And entities are represented as rectangles with the name of the entity. So staff and branch are two entities. You draw them as rectangles with the name of the entity. Then relationships are shown as arrows between entities, and it indicates there's a relationship between the two. You use a verb to describe the relationship. So in this case, branch has staff, and you have an arrow indicating the direction of the relationship. Typically, that arrow, you'll have what we call the degree of the relationship. Okay? And in this case, it's one branch has many staff. So you typically draw the arrow toward the many part. Okay? Or another way is you draw the arrow toward the entity that has the foreign key. Okay, so when drawing an arrow, so relationships, when drawing arrows in a relationship, draw the arrow toward the relation that A has many occurrences, and we'll describe that in a moment, or B has the foreign key. For that relationship. Okay, so with branch has staff, if you think about it, you have the staff relation. And in the staff relation, every staff has a branch number. But if you look at the branch relation, the branch relation does not have staff numbers in it. Therefore, we draw the arrow from branch to staff, because staff is what has the foreign key. Okay? It's also the one that has many occurrences. There are many staff per branch. So important things with relationships is use a verb. Okay? Use verbs to name relationships. Do not duplicate relationship names. Which I see a lot because it's just hard to find unique names. But if you're trying to talk about your relationships in a meeting, it's very good to have them be uniquely named. Okay, and then I already just told you that when you're drawing the arrows, you need to draw them in a meaningful way. Okay, so think of your entities typically are nouns and your relationships are verbs. Okay? So we talk about the degree of a relationship as the number of entities participating in the relationship. Okay, so it could be binary, ternary, quaternary. Here's a binary relationship. It's only between two entities. So a private owner owns properties for rent. Here's a ternary relationship. Staff registers a client at a branch. Okay, or a guest books a room at a hotel. Or a lease, I don't have it, but a lease is a relationship among a property owner, a property, and a client. A client leases a property from a property owner. Okay? Notice you use a diamond for anything more than a binary relationship. So if it's a binary relationship, you just use a line with an arrow. But if you have more than two entities in a relationship, you use a diamond. The diamond contains the name of the relationship, and then you have undirected lines into the diamond. So you only direct the relationship if it's binary. If it's above binary, the degree is greater than 2, then the lines are undirected. Now, there's always typically a lot of confusion about when something is a relationship. That's where I often find it helpful to write out the entity and its attributes. Because often when you do that, you start to find foreign keys, and the foreign keys are what tell you whether something is a relationship. So if you remember with the booking, you had hotel, and you had hotel number, and you had some additional information. And you had a guest, and you had a guest number, and you had some additional information. And you had a room, which had a room number, a hotel number, and it had some additional information. And then you had booking, and a booking had a hotel number, a room number, a guest number, and some other information. So you would strongly suspect, based on these 4 relations, that booking is a relationship. And the reason is it's chock full of foreign keys. And in fact, you would pretty much know from these foreign keys that hotel, guest, and room must be the 3 entities involved in this relationship, because they all have their foreign keys sitting in the booking relation. So when you're trying on the homework to create your ER diagrams, the biggest problem you're going to face is what are your relationships. And I find it's often useful to start writing down what I think the relations would look like and what the attributes would look like. And where I see a whole bunch of foreign keys in a relation, I know, hey, that involves a relationship. A foreign key is a relationship. So I have to somehow represent that in my ER diagram. Okay, now, here's a big, don't do this to show a relationship whose degree is greater than 2. You use a diamond. You do not use a thing that looks like this. If you draw it like this, it looks like booking is an entity, not a relationship. Booking is a relationship. It is not an entity. This makes it look like booking is an entity that has 3 two-way relationships with guest, hotel, and room, and that is wrong. In fact, a guest books a room at a hotel. It is a relationship. So that's, like I said, the biggest issue you're going to have is a lot of times you're going to try to write or draw a relationship as an entity when it's not. Okay, here's a 4-way relationship. So a solicitor arranges a bid by a buyer, and that is supported by a financial institution, for example, a mortgage institution. So you actually could, in the dream home, if this was a realtor, you might say realtor arranges for a buyer to make an offer on a home supported by a mortgage from some bank. So this would be a four-way relationship. Yes?
Are there generally like limits on like how many things should be like?
In a relationship? No.
Okay.
So that's what makes relational databases sometimes a bit hard to manage, is that sometimes the relationships get a bit unwieldy. That said, it would be rare for the degree to be greater than 3 in a relationship. Certainly not on the homework.
Okay.
The most I will give you on a homework is a degree 3 relationship. Okay. So it's not impossible for you to get up to like degree 5 or degree 6, but it's a little bit uncommon. Okay. You also can get what are called recursive relationships, and that is where the same entity is involved twice in the relationship. So for example, you have staff and someone supervises or has a manager. So in that case, the staff has a relationship with itself. Okay, so I might have, to show the relation, I might have staff, and it has a staff number, and that staff has a manager. Okay, well, this would have a staff number, and the manager would be a staff number. So this is an example of a relationship that's recursive because it's with itself. So we show it as an arrow to itself, and you assign roles to each side of the relationship. So here we have a supervisor supervises a supervisee, or a manager manages an employee. Okay, so it's an arrow coming back to itself, making it a recursive relationship. And when you have a recursive relationship, you put role names on each of the two sides of the arrow. And it should be directed. You can also have two-way relationships. These aren't recursive, it's just you have a relationship in each direction. So here I have staff manages a branch, and a branch has staff. If you looked at the corresponding tuples, you would see that a staff has a branch number, a branch has a branch number, and a manager. That manager would be a staff member. So this is a two-way relationship. So the branch has a foreign key for staff, so the relation is directed toward branch because branch is the holder of the foreign key. And then in this direction, branch has staff because staff has a branch number in it. Questions about that? Okay. So we have entities, we have relationships, and the third thing we need to identify are the attributes. And that's normally pretty simple. You normally have things like forms that you can look at that will give you the attributes, or you will do interviews with people and you will find out what information needs to be stored. So an attribute, a property of an entity or relationship type, it is normally descriptive. There's normally two types of attributes. There are descriptive attributes, okay, provide descriptive information about the entity, and there are identifying attributes that provide unique or provide information that uniquely identifies an entity. So, as you might imagine, identifying attributes tend to be keys. Okay, so descriptive attributes provide descriptive information about an entity, such as their name, their birth date, their job classification code, their salary. Whereas identifying attributes uniquely identify an entity, their personnel number, their first and last name. Descriptive information frequently changes. Your salary may change. Your job code may change. Your identifying information should not. It should be stable. So the book talks about stable and unstable. You would say that in general, descriptive attributes are unstable. They change with time, whereas identifying attributes are stable. They tend not to change with time. Okay? So the book made that distinction between unstable and stable. You can have either simple attributes or composite attributes that are composed of multiple components. An example of a composite attribute is a name, a full name, first, middle, last. That's a composite attribute with 3 sub-attributes or simple attributes. An address could consist of a number, a street suffix like lane, road, boulevard, a zip code, a city, a state. So composite attributes, address, and name are examples of composite attributes. We also make a distinction between single-valued attributes and multi-valued attributes. Okay, so a multi-valued attribute might be you have 3 phone numbers or 4 phone numbers. That's a multi-valued attribute. If you have multiple email addresses, that would be a multi-valued attribute. If, let's say, we have an employee and their children, children would be a multi-valued attribute. Okay? Keys are obviously single-valued attributes. Your date of birth is a single-valued attribute. Okay? Your date of birth, is that a multi-valued attribute? I'm sorry, let's now go. So a date of birth is a single-valued attribute. Is a date of birth a composite attribute or a simple attribute? Let's have a vote. How many of you think that a date of birth is a simple attribute? Okay, throw them up. We're good. Okay, how many think it's a composite attribute? Okay, it's about 2 to 1. The answer is it's a composite attribute. And the reason it is month, day, year. So a date of birth is 3 simple attributes, a month, a date, and a year. So it's a composite attribute, but a single-valued one. So don't confuse the two. These are single versus multi-valued, simple versus composite. They are orthogonal. Okay, by the way, multi-valued attributes tend to show up in their own relation. So multi-valued attributes, okay, typically show up or are represented in a separate relation. So relationships can end up as a relation, multi-valued attributes can end up as a relation. Okay, normally, so for example, children, because we can have one or more children, you would probably have a separate child relationship with the staff number and then identifying information about the child, say first name, last name, date of birth. Okay, I know it's a touchy issue these days, but you still typically would have gender. Okay, so this would be, child would not necessarily be considered an entity in this case, although you might consider it as one, but it's definitely its own, it's like a multi-valued attribute. Another one might be, say, phone numbers. So phone, you might have staff number, phone number, like that. So phone would be a multi-valued attribute. So what I'm getting at is relations are not always an entity. A relation could be an entity, it could be a relationship, it could be a multi-valued attribute. And then another type of attribute is a derived attribute, one that is not physically represented in the entity, but could be derived in some way. And there are three types of attributes that are derived. And I don't have a slide for it, so I'm going to have to write it down. Or actually, I could create a new slide. So let's do that. Because I have it in my notes. So temporarily, I'll create another slide. Wow, too big. 54 font. Love it. Let's make it a 20 font. There we go. Now let's make it 24. Okay. So, derived attributes, first of all, they typically end up in views because they're virtual. They're not physically represented in the database. And then there are typically three types of derived attributes that we care about. Oops. Okay, so we have aggregate attributes, things like total staff count or the min of something or the max of something. So these are attributes derived from one of the 5 aggregate operations: min, max, count, sum, average. Then you have attributes that are computable from 2 columns in the same relation. So for example, in the booking relation, you might want the duration of a guest stay. But you don't physically represent it because you can calculate it by subtracting date from date to. If you say date to minus date from, that will give you the duration of a guest stay. So you don't need to represent that information explicitly because it's redundant. You don't like to store redundant data in a relation because it could easily get inconsistent. If I updated the date to and forgot to update the duration, I would be inconsistent. So instead, we leave duration as a derived attribute. Then the third type of derived attribute is one computable from columns in 2 different relations. If I want to know the revenue generated by a guest stay, then I need to know both the duration of the guest stay and I need to know the price of the room. The price of the room is in the room relation. The duration of the stay is in the booking relation. So I need information from two different relations to compute the cost or the revenue we get from a guest stay. So the third type of attribute is one computable from columns that belong to different relations. Okay, these are all derived attributes. Okay, so how do we show all of this in an ER diagram? The answer is we often don't really show the attributes because they clutter everything up. But if you do, there is a way to do it. So the primary key is shown with a PK next to it. And if it was a multi-valued one, you'd have PK next to each of them. Then derived attributes have a forward slash in front of them to indicate they are a derived attribute. Composite attributes, you have the name of the composite attribute and then its subcomponents. And multi-valued attributes, you use brackets to indicate the minimum and maximum possible number. If it is infinite, you use an asterisk or star to indicate an unbounded number. In a actual, when you realize this, when you map this entity branch to a relation, address would not appear in the columns. Instead, you would have street, city, and postcode. So what you see in an ER diagram is not necessarily exactly what you see in a relation when it finally gets mapped into a relation. The ER diagram is higher level. It has information that may be omitted from the relation. So address will not show up in the branch relation. Instead, the three attributes that comprise it, street, city, and postcode, will show up. Similarly, in the actual database, telephone number will not show up in the branch relation most likely, but instead there will probably be a separate relation for the phone numbers. Okay? Similarly, total staff will not show up in the staff relation because it is a derived attribute. Okay? The book adds another one for foreign key. I am fine. So let's see here. I don't see anything that is a foreign key because we don't have it. In fact, in this diagram, we're not explicitly showing foreign keys because the foreign keys are shown as relationships. So in this diagram, all we're showing is descriptive attributes and identifying attributes. Okay? I might have actually gone back with the attributes here and said that a third type of attribute is a foreign key. So maybe I should have said, well, it is an identifying attribute. Yeah, they are. Foreign keys are identifying attributes. But you might say that a third type of attribute is a foreign key. Okay, provides a link to another entity. So I might have said that a third type of attribute is a foreign key, then that type of attribute does not actually show up in the ER diagram because that is represented as a relationship. So foreign key attributes would not be shown. You'd only see descriptive attributes and identifying attributes. Questions about this? Okay. So then the book talks about certain entity types. First of all, there are so-called master or independent entities and dependent entities. So the independent or master or strong entity is standalone. It stands on its own. Whereas the dependent entity, its existence depends on some other entity type. So as an example, the client might provide some preferences in Dream Home about the preferred type of accommodation, maybe apartment, condo, townhome, separated house, and the maximum rent they have. So we call this a weak entity. In a project, we might have tasks for a project. So a project is broken into tasks. The project would be the strong entity, tasks would be the weak entity. So the tasks have some existence, but if you delete the strong entity, which is the project, the task disappears. So the task depends for its existence on the strong entity. We also have a distinction between supertype and subtype entities. And let's start with an example. Let's say at a university we have a person, and then we have certain types of subtypes: student, faculty, and administrator. So all of these subtypes have some common attributes: an ID, a name, an email address that we assign them. But they also have their own unique attributes. A student has a major, a faculty has a rank like assistant professor, associate professor, full professor, department head, and a salary. Another type is administrator. They have a job code and a salary. One thing you might notice is that faculty and administrators share salary, and in fact, you might decide to have an intermediate subtype called employee, which has salary, and then you'd have subtypes faculty and administrator that have their own unique attributes. So we say that a supertype entity is a generic grouping construct for multiple related subentities. These subentities share common attributes that are stored with a supertype, and then the subtype entities is a subset of another entity, and they have their own unique attributes. The way we show it in an ER diagram is by embedding the subtypes within the supertype. For those graduate students that will be doing a project in a few weeks, this will come into play at some point in your project. I'll just give you a clue that you might want to jot away for future information. You may want to employ super and subtypes in your database project. For the homework assignments, there is no super and subtypes. Okay, so this is just like superclass, subclass. Yes?
So when you're like actually creating the table with it, you create each like subtype as it's in.
Yes, very good. So when you're creating the tables, person would have its own table, and student, faculty, and administrator would each have its own table, and then they would each have the same primary key. So in the actual student table, there would be, in addition to major, an ID so that you could link it back to, so the student would be both in the person table, and then additional information about it, the student would be in the student table.
Okay.
Okay,
So you have like
so
4 separate tables.
four separate tables, and the primary key for the supertype is also the primary key for each of its subtypes. And in the subtype, that primary key becomes a foreign key into the supertype.
Okay.
Okay? You're welcome. Other questions about that? Okay. So now moving on back to relations or relationships, you can have relationships that have attributes. And when they have attributes, you denote it as a dashed line leading to what looks like an entity, but you see that the entity is not labeled here. The name is empty. And all you have is a set of descriptive attributes. So you would not typically have identifying attributes, just descriptive attributes for the relationship. So here, newspaper advertises properties for rent. Now, anytime a relationship has attributes, you can bet your bottom dollar it will appear as a relation in the database, because you will need a table in order to represent those descriptive attributes. Also, notice that while I have an arrow here, this is what is really a many-to-many relationship, because a newspaper will typically advertise one or more properties for rent, but we may well use multiple newspapers to advertise a property for rent. So we could have also said a property for rent is advertised in a newspaper. We could have made the arrow point that way. But in general, one way you can use an action verb, and in the other direction you would use what are called to be verbs, indirect verbs. So when you have a many-to-many relationship, you have the arrow point in the direction of the action verb. So now we have constraints on relationships. Okay, and the first type of constraint is called multiplicity. It's the number of occurrences of an entity in a relation. So here, and multiplicity is made up of cardinality and participation. Now the book talks about maximum and minimum participation. I call them cardinality and participation. Participation is the minimum number of occurrences in the relationship. Cardinality is the maximum number. So please use my terminology rather than the book's, because the book is using maximum participation and minimum participation. That's fine. I use participation and cardinality. Okay? The way you represent a relationship is participation rate is first, then ... then the cardinality. So this means a minimum of 0 and a maximum of 1. So here we say that a staff may manage a minimum of 0, so many staff don't manage any branch, and a maximum of 1 branch. A branch is managed by a minimum of 1 and a maximum of 1, meaning all branches must be managed by exactly 1 person. Okay? If we have an unlimited number, then we say star. Okay, so give a few more examples first. Here, we would say that a newspaper may advertise, well, let's put it down here. So a newspaper advertises properties. So a newspaper could, depending on how we say it, maybe we say it can advertise 0 to many properties. And a property may be advertised in 0 to many newspapers. Okay, if it's already leased, obviously it is being advertised in 0 newspapers. Okay, or we may have some limit. We may say that we can advertise a newspaper in at most, a property. A newspaper can advertise at most 10 properties. So then we'd write 0.10 to indicate that a newspaper can advertise a maximum of 10 properties. Maybe we've decided that we can advertise a property in no more than 3 newspapers, so then we would say 0.3 to indicate that a property can be advertised in at most 3 newspapers. Okay? So that is called the multiplicity of a relationship. We also have what is called the degree of a relationship. Okay, so there are 3 types of degrees, and it's based on cardinality. It may be 1-to-1, meaning that for every instance, say, of staff, there is 1 instance of branch. Or it could be 1-to-many, such as for 1 instance of branch, there are many staff in it. Or it could be many-to-many, as in the newspaper can advertise multiple properties, and a property can be advertised by multiple newspapers. An example of 1-to-1 would be the staff manages branch relationship. Okay? So, to talk about the degree of a relationship, we take the cardinalities of the 2. So here, in the manages, we say it's a 1-to-1 degree because the cardinalities are 1 and 1. Here in the staff oversees properties, it's 1-to-many because 1 and star. And here in the advertises, it's many-to-many or star: because the cardinality is unlimited in each case. Okay, now again, oftentimes you will get tricked into thinking that a many-to-many relationship is an entity. It is not. So this is the wrong way to show a many-to-many relationship in an ER diagram. You will be tempted to think that an advertisement, because it has attributes and is a relation, is an entity. And you will want to show it this way, as 2 binary relationships. A newspaper has advertisements and a property for rent appears in. But this is wrong. An advertisement is a relationship between the 2 and should be shown this way in the ER diagram. This makes it clear that it is a relationship between newspaper and property for rent. This does not make it clear that an advertisement is a relationship between a newspaper and a property for rent. This looks like 2 independent relationships, which it is not. So don't get suckered into thinking that a many-many relationship is an entity. It is not. It is still a relationship and is shown that way. Okay? Now, things get a little dicier when we are trying to show multiplicity for non-binary relationships. Okay, so when we have degrees greater than 2, we still want to show our multiplicity, but it's a little harder. What you have to do now is consider for a branch, when we're showing this, what happens when we have a specific staff and a specific client? How many instances of a branch can we have? So how many staff can register? Wait, let's see. How many branches are involved when one staff member registers a client? Only one branch. A client walks into a branch and registers at that branch with a staff member. So there's exactly a minimum of one and a maximum of one branch involved in registration. Now, when a client is registered at a branch, how many staff members are involved with that registration? Generally, just one, exactly one. So we write 1 ... 1 to indicate that when a client registers at a branch, exactly one staff member handles that registration. Finally, how many clients could a staff member register at a branch? Well, if they're really good, they'll hopefully register lots of clients. And if they're really bad or they're not involved in client interaction, they'll register 0. So one staff member at a particular branch may register anywhere from 0 to an unbounded number of clients. Hence we write 0 ... here. Okay? That's why I wrote here, when you're trying to figure out the multiplicity in a non-binary relationship, it helps to write all the remaining attributes out. So here I'm trying to figure out the multiplicity for C. I write out what is the degree of the relationship. If I have one instance of A and one instance of B, how many occurrences of C can there be? That's how I write it out. And I typically write it out by using concrete examples. So here, with staff and client, I would typically say, okay, if I have one staff member, S103, at branch 405, how many clients might this staff member be able to register? And the answer is 0 to many. Therefore, here I put 0 to many. So it's a lot harder, I will admit, to come up with your multiplicities for your multi-degree relationships, but it's still important. Questions about that? Okay, so we come to our last topic of the day, and that is problems that arise with entity relationship models. And there's two primary problems that arise. They're both called traps. So the first one is a connection trap. They're connection traps. One is called a fan trap and one is called a chasm trap. Okay, so we'll illustrate them. Here's an example of a fan trap. So a division of a company has one or more staff. And the division operates one or more branches. So the problem here is that how do we determine which staff is at which branch? So we might very well want to be able to identify which staff are at which branch. But if you draw, this is called a semantic net of how this relationship might be shown. You might say, okay, division 1 employs SG37 and SA9, and division 2 employs SL21, and D1 has branches B3 and B7, and D2 has branch B5. The question is, what branch does SG37 work for? The answer is we have no idea because the information gets squeezed out right here. The fan, you can either think of things as fanning out in two directions, or you can think of this as a choke point, and information is being lost at the choke point because I can't figure out which branch SG37 is. So the problem here is that the ordering of the relationships is a bit wrong. We just need to reorder the relationships so that we now say a division operates a branch and a branch has staff. So it's kind of like small, bigger, biggest, right? Small, big, bigger. The problem here was big went to small and big went to small, and that didn't work out too well. So this is just a better representation of the flow, right? A staff belongs to a branch. A staff member doesn't really belong to a division. Yes, a staff member belongs to a division, but indirectly. A staff member directly belongs to a branch. So it is better to say directly the staff belongs to a branch. The branch operates or belongs to a division. Now everything is good. We can find that SG37 belongs to branch B3, which in turn belongs to division 1. We also can still determine that SG37 belongs to D1. We haven't lost any information. Okay, so the fan traps, let's see if I have a note about fan traps, when they generally occur. So fan traps usually occur when there are multiple one-to-many relationships leaving an entity. It's not always the case, but fan traps generally occur. Notice here's a one-to-many relationship. Here's a one-to-many relationship. That's often when you get into your fan traps. So a fan trap, to sum up, is where you are showing a relationship between entity types, but the pathway is ambiguous. You lose information. Okay? Here, the pathway that's ambiguous is the staff has a path to a branch, but given the way you've modeled it, you can't figure out actually which branch the staff member belongs to. So it becomes a fan trap. The next problem is a chasm trap. So here's an example of a chasm trap. A branch has one or more staff, and a staff oversees 0 or more properties, and a property may be overseen by at most 1 staff, but potentially 0 staff. So it looks as though there is an unbroken path from a branch to a property for rent. And it looks as though we can determine what a property, which branch manages a property for rent by saying, okay, the property for rent is managed by this staff, and this staff belongs to this branch. Therefore, we can get the information through a transitive relationship. So we draw, again, a semantic net, and we see property A14 has no staff member managing it. Oops. We can't determine which branch is overseeing PA14. The chasm, we dropped off the cliff. We start walking toward the staff, boom, into the chasm. Okay, we drop off of the cliff, hence the name chasm trap. Okay, what is the problem? The problem is right here with this 0. It looks like all the way there is an unbroken path, this 0 right here breaks the connection. So that's the problem in a chasm trap situation. There is a 0 in the participation rate. So chasm traps occur when there is a 0 in the participation rate on what appears to be an unbroken path. So a chasm trap, going back for a moment. So the model suggests the existence of a relationship, but the pathway does not exist. So what I could say is there appears to be an unbroken path between two entities, but somewhere on that path there is a 0 participation rate. Making that bigger so you can read it. There appears to be an unbroken path between two entities, but somewhere on that path, yes, I know I misspelled it, there is a 0 participation rate. Fixing chasm traps is a problem. One way to fix it is to add another relationship, in this case, a direct relationship between branch and property for rent. So we have a direct relationship, and in every property for rent, now not only do we have a staff number, but we also have a branch number. Okay, this fixes the problem. So for every property, we now have a branch directly managing it. The problem is it introduces a potential update problem. So we might have we now have a property for rent. We have P001 is managed by staff 10 at branch 1. Okay? And we also, wait a minute. Yes, we have the, okay, so now we also have staff S010 at branch B1. Okay? Now we move S010 to branch 5. What's the problem? There's a problem. There's some inconsistency now in our management data. What's the inconsistency? We moved S1 to branch B5. What if we ask what branch is managing property P1? It's wrong. So the problem is, in fixing the chasm trap, we introduced redundancy into our database right here. And if we update the staff's branch number, we have to make sure we also update it in the property, or we have an inconsistency. So the problem with chasm traps is they're not as easily fixed as fan traps. And a better way to fix a chasm trap is generally to ask if we can use a default value, thus changing the 0 to a 1. So the easiest and best way to fix a chasm trap is to ask whomever we're designing the database for, can we use a default value here? So if no one is managing this property for rent, could we just use the manager of the branch as a fill-in and thus turn this into a one-to-one relationship? Okay, so the best way to fix chasm traps is to fix the participation rate so it has to be a 1 and use a default value for those cases where we would ordinarily want the participation to be 0. Okay, that's it for today. On Tuesday, we're going to go through an actual example because what I find is when you try to do this on the homework assignment, you make a hash of it if I don't go through a concrete example in class. So we will go through a concrete example in class. If you have a question for me,